Okay, we're going to go through the notes for Chapter 5, Section 1. So this would be 5.1 in your book and in your notes. Recall that Rutherford's model, the atom's mass is concentrated in the nucleus and electrons move around it. So this is review from Chapter 4. Also, this model doesn't explain how the electrons were arranged around the nucleus. So we talked about the electrons, we talked about the fact that they're arranged around the nucleus, but we did not talk about the fact that the electrons occupy certain orbitals around the nucleus and there's a specified area where they reside. Um, Another thing is if we have this strongly positively charged nucleus and we have these negative electrons, why aren't the electrons pulled into the positively charged nucleus? Why do they remain in a cloud around the nucleus? So those are some of the things that we're going to investigate during section 5.1. Again, in the early 1900s, when they were doing all the work with the atomic models and everything, scientists observed certain elements emitted visible light when they were heated in a flame. And this light emitted, it showed a certain chemical behavior for the elements. And it's actually almost like a fingerprint for those elements. Visible light, this is a type of electromagnetic radiation, and you might not think of light as radiation, but it actually is, and it's a form of energy that exhibits wave-like behavior. So we need to understand waves before we can fully understand this model. These are the characteristics of the waves that you will need to know. Definition for wavelength is the shortest distance between equivalent points on a continuous wave. The frequency is the number of waves that pass a given point per second. And the amplitude is the wave's height from the origin to the crest. So let's look at an actual wave and see what those are. So you can see that the wavelength is the distance between these 2 points of a wave. So the crest of this wave and the crest of this wave, that is a wavelength. It can also be measured from the bottom of the wave, which is called the trough. And that's not as common as measuring it from the crest, but it should be the same distance. So it's a distance from the trough to one trough. And then the amplitude, this is the height of the wave. So we see the amplitude right here. It shows us how high the wave is. And we could draw amplitude over here. And we can draw amplitude over here as well. The only thing that isn't discussed in this is frequency. Frequency is the amount of times a wave passes a given point. So you got to consider this wave is moving through space quickly. It's actually moving at the speed of light since it's a light wave. And if I were to put an imaginary dot right here, well, it's not imaginary because I put it there, but let's pretend there's a dot there out in space and waves are traveling through it. The amount of times this wave passes this given point is the frequency. So if I have a longer wavelength like this versus something with a shorter wavelength like this one is going to have a greater frequency than this wave right here. The reason so basically the correlation between wavelength and frequency is the shorter the wavelength, the higher the frequency, or the more times a particular wave will pass a given spot, in space. Okay, so I just talked to you about waves and how they move. They move at the speed of light if it's electromagnetic radiation. And this is the longer the wavelength, the lower the frequency, the shorter the wavelength, the higher the frequency. So that's what was just illustrated on the previous slide. Sunlight contains a continuous range of wavelengths and frequencies. It's called a continuous spectrum, and it's a visible light spectrum. It has all the colors of the spectrum. That's why when it rains, raindrops act as a prism, and when the sunlight goes through those raindrops, you see a rainbow, which is all the colors of the rainbow, which is called a spectrum, and it's the visible spectrum. So the visible spectrum, visible portion of the spectrum, I like to say that it's Roy G. Biv. This is the visible. Okay, so that's a visible spectrum. The, this stands for red, orange, yellow, green, blue, indigo, and violet. Red has the longest wavelength. So the longest wavelengths, by the way, that's the symbol for wavelength right there. And violet into the spectrum has the shortest wavelength. So basically, violet light is more penetrating and stronger than red wavelength. And the reason that your eyes perceive different colors is because uh, these different colors have different wavelengths. They're all traveling at the same speed, which is the speed of light. However, the wavelengths are different, therefore you perceive them as different colors. Your eyes are and your brain are wired to perceive those wavelengths as different colors. So the longer wavelengths would be towards more the red end of the spectrum. The shorter wavelengths would be more towards the blue, indigo, violet end of the spectrum. But that is a visible spectrum, and the entire spectrum is called the electromagnetic spectrum. That includes all forms of electromagnetic radiation, visible and invisible. Most electromagnetic radiation we can't see. So things like microwaves, X-rays, that sort of stuff, these that are listed on here, we can only see a very small portion of this electromagnetic spectrum, which is just this right here. And they've, enlarged it. So this is our Roy G. Biv, and it's a continuous spectrum. One color fades gradually into the next. It's not like you say, okay, this wavelength is red, this wavelength is always yellow, this one. It's a range. So it fades from red to reddish orange to yellowish green to green blue, and so on all the way across the spectrum. The majority of electromagnetic radiation is invisible to us. It exists. We can detect it with other types of equipment, but it is not visible. Radio waves, okay? If we have a receiver, we can hear radio waves. That's how radio stations broadcast. You have to have a special transmitter though, and you have to have a special receiver in order to translate that into something audible that we can understand. You can't just hear radio waves that are traveling through the air. They're everywhere right now. If you could hear them, you'd be going crazy because you could hear everything. Microwaves, we don't hear those when it's cooking your food. We don't hear microwaves, but we know they exist because your food cooks. Infrared. Now, some animals do have infrared capabilities, like snakes and lizards and reptiles and things. They can sense heat. That's what infrared is, and it's just outside the visible range of the spectrum. Then we have ultraviolet. Ultraviolet radiation, that you can break that up into UVA, UVB. It's given off by the sun. X-rays are out there in the cosmos, but we can't see them. You can't see them traveling through your body when you're getting an X-ray at the doctor's office. And then we have gamma rays out here. So as we go from left to right across the spectrum, energy is increasing because their frequency is increasing. So your waves are longer down here than they are down here. So the shorter the wavelength, the higher the frequency, the more penetrating the waves. That's why X-rays can travel right through you, because they're highly penetrating versus visible light that does not travel through your body, or radio waves and stuff like that. Okay, light can also be explained in terms of particles. And so we know light travels as waves, but it also travels as particles. And matter can gain or lose energy only in small specific amounts called quanta. And a quantum is the minimum amount of energy that's can be gained or lost by an atom. This is Planck's constant. It has to do with the quantum of energy. We're not going to be doing any calculations with it, but basically it's the minimum amount of energy that can be gained or lost by an atom. All right. Einstein came along, used Planck's constant to describe something called the photoelectric effect. It's when electrons are emitted from a metal surface when a certain frequency of light shines on it. So metals are shiny, and we know that because when we see light bounce off of them, it looks shiny. If you have no light, the metal's not shiny. So it's not like it's giving off shine. It's actually reflecting or ejecting electrons when light shines on that metal surface, if it has enough energy. So Einstein talked about the dual nature of light and said that it was a wave-like and particle-like properties. And a photon is a particle of electromagnetic radiation with no mass that carries a quantum of energy. So light is described as photons. And this is an equation that he used to describe, incorporating Planck's constant with his energy of a photon and representing the frequency. And there's this equation that goes along with that. Again, we're not going to be calculating this, but it does exist. We're going to be looking at spectrum activity coming up here soon. And this is light in a neon sign is produced when electricity is passed through a tube filled with neon gas. It excites the neon atoms. When those atoms get excited, their electrons jump to what's called a higher energy state. When they fall back down to what's called their ground state, energy is emitted in the form of light. And each atom has a unique spectrum. So neon signs look red. Other gases of other elements give off other colors. If it's not a red sign, it's not a neon sign. It's some other gas that's inside those tubes. Okay, in order for us to see the various colors of the visible spectrum, we need to have something that's called a prism. And we're going to be doing this in a lab. You're going to have a prism. We're actually going to be having hydrogen gas or various gases in a discharge tube. And we're going to be looking through a prism. And you'll see that, let's say neon, for example. Neon is a red light, but then when you look through a spectroscope, you'll see various colors are given off. These are called an emission spectrum. This is the emission spectrum for hydrogen. This is called actually a bright line emission spectrum is another name for it. So bright line emission, oops, spectrum. All right, so notice that these distinct bands are given off, one here at 410 nanometers, one here at 434, one here at 486, and one here at 656. Those colors combined, or when those three bands of light are combined, it gives off a purplish color. But if you look through a spectroscope, it separates it out into those unique bands. Every element has a unique spectral line and or a unique bright line emission spectrum. And because of that, we can identify elements based off of their spectrum. That's how we know that the sun is made up of hydrogen and helium, because scientists have viewed their spectrum, their spectral lines, and said, okay, that's the spectrum for hydrogen, that's a spectrum for helium. And we can identify what planet, or not planets, but different stars and suns around the universe consist of. Okay, so this is hydrogen's atomic emission spectrum, also known as the bright line emission spectrum, and different wavelengths correspond to various colors. The longer wavelengths are down here, the reds, the oranges. Over here we have the blues, the indigos, violets. These are the shorter wavelengths. Remember, this is the symbol for wavelength right here. Nanometers is what it's measured in because it's very small. Nanometers is 10 to the negative 9 meters. So um, it's very small. And like I said before, each element's atomic emission spectrum is unique. So it's like a fingerprint used as a way to identify various elements. Okay, we will stop here for section 5.1.